Now for an example that sort of motivates all of this from the algebra side, let C be a C-linear category, or a K-linear category if you like. Then define KC. Now I didn't really go into that, but in a K-linear category you have the notion of kernels and images and whatnot. So there is some concept of some sequence being exact or some sequence being a complex. So what are the objects in KC? The objects are complexes over C, meaning that they are sequences Cn for n and the integers of objects of C together with a sequence of morphisms Dn is a morphism in the category C between Cn and Cn plus 1 such that d squared is 0, meaning that dn plus 1 composed with dn is equal to the 0 morphism. And the morphisms in the category Kc between a complex C and a complex D of degree n is just the Cartesian product over all I and the integers of the morphisms in C between Ci and Ci plus n, meaning that we're sort of looking for linear maps that increase the degree by n. Then we have a differential operator there, a differential d from more n to more n plus 1, defined by, well, the differential d now takes a tuple of functions indexed by I, which is an integer. And what is it? Well, it's again a tuple of functions, and that is now decomposed with fi minus 1 to the power of n. And now we have I plus 1 composed with d, because d increases the degree by 1, so you need to have fi plus 1 there. And all of that again indexed by the integer I. And one can again prove that d squared is equal to 0, just because, well, the signs sort of work out in the end, and because the d's on either side square to 0. We also have a composition and that composition is just given by, well, if you compose fi, I, and z, which is an n-morphism between d and e, and g, j, which is an m-morphism between c and d, then fi after gj is going to be fi plus m after gi indexed with I and z, because gi is a map from ci to di plus m, and now we need to apply the corresponding map in this tuple. And again, one can prove that this is a DG category.